Well, good afternoon, and my thanks to everybody for joining us this afternoon at this magnificently newly renovated President's Hall for the 2013 Christopher Peebles Memorial Lecture for Information Technology. This lecture series commemorates the decades of dedicated and loyal service to Indiana University by the late Christopher S. Peebles, who was Professor of Anthropology and served as Director of the Glenn Black Laboratory of Archaeology from 1986 until his retirement in 2009. As an anthropologist, Chris was a scholar of the ancient past, but he also helped Indiana University to advance its high-tech present and future through his leadership of many information technology initiatives here. Chris liked to describe himself as an anthropologist by training, but an information technologist by avocation. And as Interim Associate Vice President for Information Technology University-wide on 2 occasions, and as Associate Vice President for Research and Academic Computing, he was at the forefront of key advances in the delivery of IT services in support of science and scholarship at Indiana University. He also played an important role in the development of IU's first IT strategic plan, which was released in 1998. In 2009, when we dedicated the IU Data Center, I had the pleasure of awarding Chris the Thomas Hart Benton Medallion for his prominent achievement and dedicated service to Indiana University. When Chris stepped down as Associate Vice President in 2003, we established this lecture series in his honor with the aim of bringing to Indiana University some of the most visionary leaders in information technology. People like today's speaker, Dr. Paul Messina. Paul Messina is Director of Science at the Argonne Leadership Computing Facility at Argonne National Laboratory. The ACLF is one of the 2 leadership computing facilities supported by the Department of Energy. It provides the computational science community with world-class computing capabilities in order to accelerate major scientific discoveries and engineering breakthroughs, among those who explore areas such as renewable energy, the effects of global climate change, and the origins of the universe, among many other areas. Dr. Messina was born in southern Italy, not Indiana. That's where I was born, of course. That's where my accent comes from. in the summer of 1943, in the middle of an Allied air raid. When he was 6, his family moved to Central America to escape the aftermath of the war. He later came to the United States to continue his education, eventually earning his master's and doctoral degrees in mathematics from the University of Cincinnati. Early in his career, he became interested in numerical analysis, and he joined the Applied Math Division of Argonne National Lab, where he worked closely with James Wilkinson, a prominent figure in the field. Between 1973 and 1987, Dr. Messina held a number of positions at Argonne, and he was the founding director of the Mathematics and Computer Science Division, which he built into a major center of research, which it has continued to be until this day. In 1986, Dr. Messina organized a workshop on parallel computing, where he met Geoffrey Fox, who, of course, is now a distinguished professor at IU, but who was then at the California Institute of Technology. Professor Fox helped convince Dr. Messina to join the Caltech faculty, where between 1987 and 2002, he held a number of positions, including serving as the founding director of the Center for Advanced Computing Research. And while at Caltech, he also served as the co-principal investigator for the National Virtual Observatory, which allows scientists to access data from multiple astronomical observations all through a single portal. Dr. Messina also served from about 1989 to 1992 as the principal investigator for the Casa Gigabit testbed, which I think many people regarded as the most visionary of the 5 testbeds that were part of the Gigabit Testbed Initiative. And Casa connected Caltech, the JPL, San Diego Supercomputer Center, and Los Alamos National Laboratory. And the primary focus of Casa was on distributed heterogeneous supercomputing applications involving very large computational problems. As such, I believe it was in many ways a very influential forerunner of the very high-speed backbone network service, Internet to grid computing to cloud computing, and much more. He also served as director of the Concurrent Supercomputing Consortium, which brought together about 13 institutions, including several federal agencies, number of national laboratories, number of companies who pooled their resources to gain access to its unique computational capabilities. And that consortium created and operated the Intel Touchstone Delta system, which was then the world's most powerful scientific computing and remained such for nearly 2 years. I had the honor to be invited by Paul to be at the opening of the Touchstone Delta system, I think in 1991. But it's interesting to remark that the system that we will dedicate tomorrow, Big Red 2, is about 100,000 times faster than the Delta was at that particular time, just over 20 years ago. The system, the Delta, was a prototype too for the Intel Paragon supercomputer, which was later sold as a commercial product by Intel. And one of these Intel Paragons was in fact the first parallel supercomputing that was acquired by IU, I think in about 1993. And during a leave from Caltech in 1999 to 2000, a couple of years, Dr. Messina led the Accelerated Strategic Computing Initiative, which was an initiative in the Department of Energy to help maintain the US nuclear arsenal through the computational testing of nuclear weapons following the 1992 moratorium on actual nuclear testing. And I think his service to our nation in this role really was maybe unsung, but really was immense as well. He led Caltech's participation in the formative first year of the TerraGrid initiative, a national grid infrastructure for high-performance computing, of which IU has been a partner. In 2002, Paul retired from Caltech, and as much as Paul's ever retired from anything. And for the next 2 years, he served as a distinguished senior computer scientist at Argonne National Laboratory and as an advisor on computing to the Director General of CERN, the European Organization for Nuclear Research, which of course is the home of the Large Hadron Collider. His work over the decades helped to make world-class computers more widely available, and it helped to lay the foundations for grid technology and to bring parallel computing technology to the forefront of scientific computing. Of course, Paul has, over many years, published extensively, but I just want to mention, I think this is a very nice connection, one of his publications, which I think has particular significance to the function that the dedication of Big Red 2 that we'll have tomorrow. In 1995, he published a book, a collection of papers called Enabling Technologies for Petaflops Computing. And his co-authors included Tom Sterling, who was then at JPL and is now, of course, Professor of Computer Science here in Informatics and Computing. And Tom also delivered the inaugural Peebles Lecture a couple of years ago. And as Associate Director of the Pervasive Technology Institute Center for Research in Extreme Scale Computing, Professor Sterling also participated in the acquisition of Big Red 2, which, as I said, we will be dedicating tomorrow. And this acquisition was spearheaded by two of Chris's successors in the Office of the Vice President for Information Technology, the current VP, Brad Wheeler, and Craig Stewart, who actually holds Chris's original position, as well as many other people who are involved in that as well. And Dr. Messina will give the keynote address at the dedication tomorrow. So Big Red 2, in many ways, is a realization of his visionary 1995 book, as it will be the first university-owned, university-funded supercomputer with a peak speed of a petaflop as well. And I just want to add on a personal note that I've known Paul very well for around 25 years, and there are few people who I admire or respect more for his vision, for his integrity, and for his service both to science and to the nation. So please join me in welcoming Dr. Paul Messina.
Thank you, Michael. Michael, thank you very much. I am nearly speechless, but I should give a talk, shouldn't I? So, given my advanced age and the fact, as Michael has pointed out, that I've been involved in this scientific computing activity for many years, decades now, I thought I would take a look back for some of the time. I'll be bouncing between looking back and looking forward throughout this talk. But I'll start by trying to explain in my words why people think that at the high end of scientific computing we're facing a transition. What's making that happen? And to look at the previous transitions that I will categorize by my own taste. What did we do then to make them successful? Look at perhaps some things that might help with the next one, and then talk about some things like the importance of software and what I see as future issues. I may have time for random thoughts. We'll see about that. Now, since I used to be a mathematician, I like to define things so we know what we're talking about. And just quickly, I wanted to make clear that when I talk about scientific computing, I'm not talking about only what we used to call number crunching. That's certainly part of it, but just as important is being able to read data, write it in the quantities we want, visualize it, store it, and retrieve it easily. So scientific computing, I think, is the entire workflow, and so one needs to worry about all those things, not only a very fast compute engine. Secondly, I see that scientific computing, at least as I've been engaged in it, is what I would call an experimental endeavor. Writing papers is part of it, but it's not enough. You have to actually implement things. That's my preference anyway. So I think of it as an experimental endeavor, and in some ways it's like an engineering endeavor because we need to build things, see if they work, adjust to make them better. And my own focus has been to work primarily at the high end. It does not mean that the smaller computers are not as useful to science, because they are, but it's different. And so that's just a road that I happen to take. So let's see. Previously, this was the advance was working. So let me try this. Okay, I'll try this way. Now, to give you an example of why I thought of the experimental approach, Michael mentioned Jim Wilkinson. Well, in the 1960s, people published articles in Information Mathematique primarily of basic fundamental algorithms for doing calculations, linear algebra, eigenvalue system, solution, and so on. But even with those perfectly well thought out algorithms that were implemented on paper in Algol 60, it took somebody like Jim Wilkinson and many others, Cleve Moeller, Pete Stewart, in the early days of Jack Dongarra's career, Jack, to take those algorithms that you would think everything had been solved, but when it came to implement them on a real computer, get the results you would want reliably, portably, understand the limitations, it took years of work by very talented people. So that's the key example that I would think of from the early days. If we just stayed with the algorithms and thought that was it, we would be wrong. Later, Ahmed Sameh, who published in the 1970s a lot of parallel algorithms, when he spent some time at Argonne where we had real parallel machines, told me he had to rethink all his parallel algorithms because when they were working on real systems, turns out that the bottlenecks, the balancing points were different from what he had anticipated. So partly because of that, in 1983, approximately, I was at Argonne at the time in the Math and Computer Science Division, and I felt that it was important for the numerical analysis work that we were doing to have an experimental facility. And so I managed to get funding to acquire a variety of parallel computers, different architectures, because I felt portability would be important. And if we just got one, we would inevitably try to tailor everything to that system. And so we had a variety of them. And since I had wonderful staff, they did all the work, the innovation, and they also taught a lot of short courses on parallel computing where people could actually use computers. And in fact, people like Bill Harrod, who is now in DOE headquarters, and leading the Advanced Scientific Computing Research Division in 1984, came to one of those courses, and he told me that's where he learned about parallel computing and it changed his career. So having experimental facilities is not the end of it, but I do like to do that. And Michael talked about the touchstone delta. Yes, I got fed up with people saying, well, parallel computers are okay for small things, but they'll never beat the big craze. And I felt it was time to demonstrate that they could by building a real one and putting real applications on it. And so on the second week of the Delta working, we were able to show off a rather complex, sophisticated application in fluid flow, where you had dynamic load balancing, you had adaptive mesh, not a regular mesh, and you could model CFD. And the reason we were able to do it almost immediately is because we had portable algorithms, and so we had developed this application and a number of others on smaller systems, but using portable software and portable approaches. Okay, so we have disruption coming. The reason is, we're at petaflops now. Of course, we've got petaflops, and we want to get to exaflops, so 10 to the 18th. And the reason is that although Moore's law continues, you can see that the green curve keeps going up pretty nicely. That's the number of transistors multiplied by 1,000 in this particular graph. But if you look at the lower curves, around 2004, they kind of flattened out. So the clock speed has improved something like only 30% in the last 9 years. In the previous 9 years, I think it improved something like 300%. So the clock speed for this particular technology, the CMOS technology and fabrication methods that we use, hit some limits. So it's the Dennard scaling, which has to do with the actual voltages and transmission of electrons that hit barriers. And because of that, now to get more power, we really have to rely on many, many more transistors, these days organized as many, many more cores and processors. So that's, in a few words, why there's a difference, because the green curve keeps going up, but the blue curve and the other ones do not. Power is the light blue curve, and that's an issue too, because it's telling us that as we increase computing power, the electrical power is going to be about the same factor. Instead of before, we might get 10 times as much speed and only twice as much electric power needed to get that speed. So that's why we're facing disruption. Well, one might ask, why don't we just settle for what we have? What's so important about going faster? Well, we tried to answer that question in mostly 2008, 2009. Department of Energy sponsored 8 workshops on 8 different scientific fields, as well as a couple of others on cross-cutting issues like algorithms. And so these are the covers. Each produce a report of about 100, 150 pages, and you can get them. They're all online. And the summary is that there are a lot of exciting things that could be done if we had the exaflops, and so there's good reason to go after it. That we have by no means run out of exciting scientific and engineering advances that could benefit from a lot more computing. In addition, I believe in trickle down. It's not perfect, but just as when we were studying petaflops in one of the meetings, Jeffrey Fox said, well, the reason he likes petaflops is because that means he can afford a teraflop computer in a few years. Well, likewise, now if we just do simple arithmetic, if it would take 40 megawatts to power an exaflop system, that means that Big Red would only need 40 kilowatts. And your electric bill would be a lot smaller than it will be over the next year. And same thing to buy it. So let's agree then we are at the very high end entering another disruptive phase. It's certainly not the first one in my view. I happen to like Gould's evolution theory of punctuated equilibrium. Now, for a long time, I guess paleologists would say that, well, evolution was fairly gradual, but then when they started looking at the fossil record, it turned out to be long periods of stasis, and then something would happen to the environment, and there'd be a very rapid evolution, reach equilibrium again, and go on. So it was punctuated equilibrium. And I think that's what's happened in computing as well. Let's assume we're about to enter another one. And so I have been these approximately in periods of years and what was important. So I'll just start with, we had serial computers, of course, but then what I would call high-performance serial were the machines like the early control data systems and some of the early IBM systems. So what were issues? So as soon as you got a fast processor, then right away you had memory problems. That is, getting data fast enough out of memory into the register so that you could get your work done. And so control data did it by partitioning memory into small and large, and then you would manually, that is, you would explicitly move your data from small to large, because small was faster access memory, but you couldn't have it big enough for what you needed. IBM instead took the route of caches, which of course are prevalent now. So different balance points, but memory access was the issue. And I like this quote from Seymour Cray, anybody can build a fast CPU. The trick is to build a fast system, and he was including I/O in that statement. Now, portability was an issue not only at the Fortran level, which was the prevalent programming language, but even at the way floating point arithmetic was being done. Those of you who may remember the way Cray used to do divisions, for example, was rather different from the way IBM did, and that meant that some algorithms would converge to different solutions or not converge. And so that was an issue too, portability even at the hardware level of how you do arithmetic. Performance portability naturally as well. One thing that helped is that in that period from the 60s into the mid-70s, a lot of libraries that were pretty good were created. I mentioned the packs that Argonne was very involved in, IcePack, LinPack, MinPack, FunPack. Fun is for special functions, by the way. But there were also companies, IMSL and NAG had very rich and very good libraries. So after a while, we started transitioning to vectors. The first vector machine, it wasn't the absolute first, but it was the first big commercial one, was the Star 100. And it suffered from being a memory-to-memory system, so you had huge delays in getting, again, the issue of moving data to where you can work on it. And since it was pipeline, if you had a long enough pipeline, then it was fast, but you had to have a very long pipeline. So unless your calculation happened to be all long vectors, you wouldn't get very good results. The Cray 1, which was partially designed looking at nuclear weapons calculations, but also weather and others, had a register-to-register architecture, but also it happened to have a much faster sequential speed. And so some of the early labs that got a Cray liked it a lot better than the CDC 7600, because even when the application didn't vectorize at all, it was just using it as a sequential system, it was quite a bit faster, about twice as fast as the 7600. This was also an era in which, not at Cray initially, but the Japanese vector systems and the small vector company called Convex had good vectorizing compilers. So for fairly regular applications that did have vectors heavily involved, the compiler actually did a fair amount of the heavy lifting. Unfortunately, it's one of the few times that compilers have been quite that useful. I also mentioned the ETA-10. That was a long vector machine which was put at Florida State University. And I mentioned that because it's an example of how scientists, when they're motivated, can surmount almost any architectural obstacle. Now, that's not a good thing necessarily, because it takes a lot of work, but because what they had was this long vector machine, and there were people who were doing high energy physics that was dominated by normally serial algorithms, some algorithms that I thought would always be serial were in fact vectorized successfully. Bill Martin at Michigan was one of the people who managed to do that. But it took a lot of work. And then came the flood of lots of different parallel architectures. I'm not going to try to mention even half of them. But one of the things that was happening early on, around 84, 85, is the common wisdom was it's the shared memory parallel machines that are going to be the winners. They're much easier to use. The distributed memory ones are just too hard to use. Certainly it's true that you needed different programming models, which pretty much quickly gravitated to message passing of some flavor, and I list some of the steps along the way. Initially, every distributed memory machine vendor would have its own version of how you pass messages to move data from one place to the other, and gradually the community got together, and in the early 90s came up with the MPI standard, which is still the prevalent way of doing programming. But initially people thought shared memory was the thing. However, it turns out it's difficult to scale it affordably to any large extent. And of course, I/O was an issue even more than ever. And so that motivated one of the projects that I initiated with many colleagues. It's called the Scalable I/O Initiative. We wanted to have I/O be as scalable as arithmetic. I would say we didn't succeed all that well, but some good things came out of it. Romeo and Pitch I/O came out of that project specifically. And then we get into the petaflops. So on the lower right is the cover of the book that Michael referred to on enabling technologies for petaflops computing. And the project that I was associated with for a while when I was in Washington for 2 years, ASCII, was one of the major movers because it set a long-term 15-year schedule for achieving first a teraflop and then 10 and 30 and then 100. And pretty much was able to do that, motivated a lot of people and companies. Not a lot of new design. It was evolutionary, which was something we were criticized for. On the other hand, we really had a schedule because of mission needs, and so we had to make do with, let's say, boring architectures, but in the end they did work. Now, high energy physics community, and specifically QCD, has from a long time been involved in helping to design scientific computers, and certainly is still doing that today. But I give some examples. The cosmic cube, it used to be that Jeffrey Fox was interested in QCD, and that was one of the reasons that he and Chuck Seitz put together the cosmic cube. But then other systems, including part of the design for the IBM Blue Gene series, which we have a copy at Argonne nowadays. So that takes me into co-design. It would be nice if we could have a clean sheet, but in the early days, almost did. Livermore worked very closely with IBM on the LARC, Los Alamos with the Stretch. Cray in the 70s spent a lot of time talking to people at the nuclear weapons sites and climate sites. And things like gather scatter came out of looking at the actual pattern of computing you needed to do. I mentioned GRAPE, and Velka Han, who was a professor at Berkeley, used to be at Toronto, did something that I believe was very important. I mentioned earlier that arithmetic wasn't being done the same way depending on which brand computer you had. And Vel, through persistence and very good design, managed to get the community behind the IEEE floating point standard, which initially some of the vendors resisted, but in the end was adopted. Not everybody loves it, but like most standards that are useful, it doesn't have to be the most beautiful. It does have to be the most ubiquitous. With the Intel Touchstone Delta, we also didn't have a clean slate. We knew we were going to use an i860 processor, for example. And we decided very early on that we would use wormhole routing chips that were designed by Chuck Seitz and and a student called Bill Daly, who some people know in a different way these days. But the thing that we, at Argonne and Caltech, I was at Caltech, but Argonne participated in this, we would have meetings every month for several days in Beaverton where the machine was being designed. And we mostly focused on the software because there we could influence it more, although we did influence the configuration. Again, guess what? Worrying about I/O, being able to get data in and out, but also on the software. And the usual thing we found is we would tell Intel, look, give us a few software tools that are simple but actually work. Do not design really fancy software tools that don't work most of the time or are hard to use. So in other words, keep it simple. We'd be happier as scientists having a few basic things that we can trust as opposed to something that sounds very nice but probably doesn't work all that well. And so that was co-design, and it did result in the Touchstone Delta, which for a while was the world's fastest computer with a peak speed of, hold your breath, 13.9 gigaflops. Amazing. I wish that we could have revolutions, and maybe towards the end of the talk I'll indicate some things that, well, not brand new revolutions, but maybe not quite as evolutionary. But I still think we should try to move in this direction of influencing products. My experience is that vendors will listen. You have to be patient, and you have to realize that you have to talk 2 generations out. The next generation, it's already too late to influence. But you can do something. And so long as you set the sights of being realistic, which I would say is, let's at least try to make it better than it would have been otherwise if we didn't talk to them. It won't be what we want necessarily, and we won't be able to get them to adopt a completely new microprocessor, I'm guessing. But there's a lot we can do, and so I believe that's important. And one part of co-design is on us. As we get a feel for what the vendors will be building, what the architecture will be like, what the programming model will be like, we can start now to think about how to modify our mathematical algorithms and the models and the tools as well, the software tools, the compilers. So a lot of the evolution has to be in that part of the environment. And I won't read through all of these examples because you probably know them as well as I, but there are a lot of applied mathematics algorithms that have been adapted to deal with the new trade-offs, such as that you can have a lot of arithmetic, but maybe it's still hard to get data to the arithmetic unit. Now, in the lower right, I mentioned novel algorithms. People talk about reduced precision arithmetic algorithms because there you're storing fewer bits. That means you have to move fewer bits. So again, data movement being so important. But you want to maintain accuracy. And so since I'm involved in looking at the history of computing at Argonne, I thought it might be amusing to show you FLIP. This was a computer that was designed and built and worked at Argonne in the 1960s. And so what did FLIP do? A floating index point computer. It provided a way to measure the accuracy of algorithms as they were executed so that afterwards you could analyze what the accuracy was, and based on that you could decide what precision to actually use, because there was a mode in which you could tell FLIP only use this many bits. So it's a nice concept. Just wanted to point out it's not exactly new, but it was probably forgotten for a while, and that's something that happens not only in our community, but it does happen in our community. We forget things that actually were good ideas, they worked, but somehow they get forgotten. Anyway, that's FLIP, and people looking at an oscilloscope as they were doing some tests. Now, I want to quickly look at, well, what has been the payoff, over the last few decades in applications. Of course, there are dozens of them, so I only deal with a couple. I do want to point out, though, that certainly, although the applications I will show took advantage of the greatly increased memory size, computing speed, in every case that I'm aware of, it wasn't just a brute force. It also required improving algorithms or coming up with new ones. So cosmology is one that is a little bit easy to map, both because I knew about some projects, but also the numbers are easy. So John Salmon and Mike Warren, in the very early days of the Delta, got a Gordon Bell Prize in 1992 for performance. You know, the most performance, they actually achieved 5 gigaflops out of the 13.9 by simulating 9 million gravitating stars. 5 years later, Salmon and Warren, along with Thomas Sterling and a couple of others, got 2 Gordon Bell Prizes. One was for performance, and that was for simulating 322 million now particles. But they also got, by using a Beowulf system, the Price Performance Prize for a smaller problem there, 10 million particles. So I thought that was amusing. And of course, you know, the book and all the courses that Sterling and Salmon and others, Don Becker, gave had a big impact. And more recently, partially at Argonne, partially at Lawrence Livermore, Salman Habib, who is a cosmologist, has run on Sequoia, which is the Livermore system, 20 petaflops, and on Mira, the Argonne system, which is a mere 10 petaflops. And on the Sequoia system, achieved 14 petaflops. That's 14 million gigaflops, right? And on a half-size machine, was able to get 69% of the peak speed. Now, I'll come back to that peak speed issue a little bit later, but I wanted to point that out because it isn't just scaling that matters. You also want to actually get some performance out. So it does scale well, 90% parallel efficiency, but the key thing is it got a very large fraction of the potential peak speed, and it's a real application. It's not just to keep the processor warm, but they are doing science. They did require a new tree algorithm, so as did Salmon and Warren earlier in their work. And they're producing a lot of data as a result of this simulation. So far, it's over 6 petabytes. That's an old number. I forgot to update it. But so those simulation results will be made available to the community. And that's a theme I'll get back to shortly. Yeah. Large simulations, just as experimental data from, say, particle accelerators or microscopes, it's important in some cases to keep them, archive them, and make them available to the community. A different kind of application, you can see through these 3 images what difference resolution makes. So on the left pane, that's 36-kilometer resolution for a study of the year 2005 hurricane season in the western Atlantic, in other words, near the United States. So 2005 is the calendar year that in recorded history has had the most hurricanes and the most Category 5 hurricanes. That was the year of Katrina as well. So you can see at 36 kilometers, so there on the left, doesn't look that much like a hurricane. At 12 kilometers in the middle, starting to look like it, but when you get to 4-kilometer resolution, that particular simulated hurricane looks a lot like a hurricane. Furthermore, by running through the whole simulated 2005, Greg Holland at NCAR even got a much better result in terms of how many Category 1, 2, 3, 4, 5 hurricanes happened during the season. At 36 kilometers, for example, it showed nothing greater than Category 2 and only 2 of them. So this is not only a way to get better individual hurricane simulation, but even on a climate basis for the year. So that's an easy one to grasp. And then the last of this type that I'll mention is in biology. Dave Baker at University of Washington, the father of Rosetta, also uses very large systems. And so here I just traced from 2007 when he started using the Blue Gene L at Argonne and got a mere 5 million core hours awarded through the DOE Insight project through 2012. And you can see that, at first he could replicate some known results. So that's, 2007. So it wasn't new science, new discoveries, but at least he was getting pretty good at replicating them. Then he, as is shown in the red type there, came up with some new algorithms, new ways of looking at the NMR data, and was starting to be able to develop some previously unknown structure and using less data. And he proceeds to the point that he's able to deal with some very large structures. And along the top, you see the word nature, science, and nature. So those are papers, and those rather influential, high-impact journals. So this was clearly important science that was getting done, and in a field that we don't often think of as taking advantage of the very big machines. But these are not all just millions of small programs executing. In some cases, he's actually using a reasonable fraction, not the whole machine, but a reasonable fraction of pretty big machines. So there's that kind of benefit to science through bigger systems, more powerful systems, more memory, faster CPU units. But then there's also the technology push. And so, well, you already know the story because Michael told most of it. But in 1988, Bob Kahn, who was one of the fathers, the real fathers of the ARPANET, came to visit me and basically said, Paul, what would you do if I provided access to you to a gigabit per second network over a fairly wide area, say 2,000 kilometers, and and you could have it for a few years to play with? What would you do with it? And so I thought about it, talked to some colleagues, and that's how the Casa Project got started. So Bob was able to get funding from DARPA and NSF for that project. 5 test beds were put in place. Mine happened to be called Casa. And so what I thought is, well, if we go to Los Alamos, San Diego Supercomputer Center, Jet Propulsion Lab, and Argonne, we'll have quite a bit of memory, quite a bit of disk space, and quite a bit of computing power. So let's try to use those for some real applications, not toys, but applications that people will care about the results of. And after some investigations, came up with 3. One was chemical reactions with Aaron Cooperman and his students. And there the idea was that since part of it, of his calculation, was mostly eigensolving, and that did not parallelize very well, but it vectorized well. But some of it was more solving systems of linear equations, and that we could parallelize really well. How about if we put the algorithm that was best on the architecture for which, at least in that implementation, it was best? And so we had part of it running on the Delta, part of it on the biggest cray at the time at San Diego, and we'd use the network and pipelining. And so we were able to hide for half an hour all but about 30 seconds of the data transfer and achieved super linear speed up that way. So that was one. We also did a combined ocean and atmospheric climate model. Roberto Mechoso at UCLA was our partner for that. And then the application that I actually like better than even those 2, although those were very nice, which was interactive access to 3 different kinds of large data sets stored in different places and being able to visualize and explore them interactively. So you've got the seismic data, so that's the vertical direction. The false color is from Landsat data. It tells you the mineral composition on the surface, and then you got the topography data, the hills and the mountains. And so Ron Blum at Jet Propulsion Lab, who was a geophysicist, and others worked with us to demonstrate that he could explore and do cutaways, such as the one that's shown here, interactively, and get information by looking at all 3 of the data sets simultaneously, information and insights that he couldn't do any other way. So I view this as an early example of the type of thing we talk about these days with big data. It's not exactly the same, but it's certainly in that direction. And as Michael said, you know, Ian Foster and Carl Kesselman came to visit me after a couple of years and said said, well, you know, the Casa thing was nice, but, you know, your software stinks, which it did, because it was an early experiment, if you will. So we didn't have close scheduling automatically. No, we would say, yes, on Saturday morning for 4 hours, we're going to have all the machines on Casa available for these experimental applications. We did extend the programming model some so that, you know, you'd have only one program that would spread itself over the different systems, but it was pretty crude. But that was fine. I said to Ian and Carl, do it, absolutely, because I'm not good at that, you are. And so that led to a few other things. So about a decade after Casa, I was fortunate to get involved in what was the Natural Virtual Observatory, which has now also spawned an alliance of 19 members of different world regions. You know, so there's, you know, the European Union is involved, but also countries like, you know, France and Germany individually, Australia, New Zealand, I believe, Brazil, United States, and the idea is that, you know, there are all these all-sky surveys in different wavelengths at different times, you know, so digital, infrared, and so on. And wouldn't it be nice if they were available online? Well, we have enough storage, networks was fast enough, and there was, you know, pretty good database technology to be able to do queries that involve several different databases simultaneously. And the idea was you'd be able to make new discoveries out of data that had been known for 50 years or more, like the Palomar All-Sky Digital Survey. And so you can see in the one example then towards the bottom there, in infrared, you can see a new galaxy that's very close, you know, only 30 million light years away, and the optical, you really can't see it at all. Or an example that I like better is this one, the same thing, the Crab Nebula. If you look at it in X-rays in the top left, you know, versus optical on the top right, and infrared, you know, it looks very different. So being able to see an object in different wavelengths really does matter. And in fact, astronomy discoveries have been made through this kind of observatory. So this is experimental data, but accessed in very flexible ways, and you can do it anywhere you are in the world. We used to talk in the early days of this as we want to democratize this science, so you don't have to be at a place like Caltech that has a long history of telescopes, you know, the Palomar and the Keck and so on. You can be anywhere in the world, and if you've got the initiative and you know what questions to pose, you might do some new science. A different kind of repository I mentioned with Cosmology, but, you know, climate simulation data is being stored and made available, such as the hurricane data. I possibly forgot to mention. Greg Holland makes that available, and anybody can download it from NCAR and do their own analyses of the data. Seismologists are doing that, and Habib is planning to do that. So, so how is it that people make progress? Often in the last several decades, it's taken a team of people. So this is a little bit sarcastic, but here's my fable of how it is that people from different disciplines can work together and get things done. So, you know, assume that, you know, there are people that have the right interests, the right skills, expertise, and ideas in computer science, domain science, maybe engineering. What seems to make the difference is that somehow one puts in place a structure that enables them to crystallize and work together. And there are, you know, a number of domains and the projects in which that has happened. Often it's a long-term project that has a very appealing goal, and so that gets people excited enough to work with each other, even though initially they speak a different language. And so in my fable, such a structure happens, people actually do things they're excited about, they publish, and the last part is a tough one. They manage to have a good career, even though they're participating in a multidisciplinary project, where their own contribution is going to be difficult to identify and even to judge if it is identified. So that, and furthermore, they'll publish less. And when they do publish, you know, there might be 30 authors. That's tough, and yet it's a way of doing one type of scientific discovery that I don't know how to do any other way. But it's hard to get people to do that, to choose that as a career because of these drawbacks. It's not such a good career path yet. Well, I know that I'm running a little bit long, so I will hurry a little bit. I think you all know software is infrastructure, and because people have put together community codes, groups like the Lattice QCD community have come together and really organized themselves well. They've been able to do things that I don't think would have been possible to do otherwise. And so all that software is as much infrastructure as hardware, in fact, more so, has a longer lifetime. Sometimes, if things change enough, you want to start from scratch again. So in the case of chemistry, something like 15 years ago, a group of people led by a Pacific Northwest lab did NW Chem, and it's still going very strong. But then one of the people, Robert Harrison, a couple of years ago decided it was time to restart from scratch, and so he's developing a framework called Madness. It's possible to do that, and the ASCII codes were able to do that, and the last cosmology code that I talked about, which is called Hack, is also a new start. Someone decided to start from scratch. And so I say, well, you know, with infrastructure, we can do that. So here's the Bay Bridge. You know, on the left, you can see the older bridge, which is the one that was damaged by the earthquake, and the new one is now in place. And in 2015, the old Bay Bridge will be torn down. So there'll be this period of, you know, several years of concurrent bridges, the old one and the new. And so it would eventually do away with the infrastructure. So community codes, I think, are very important. And at Argonne, one of the ways that people can use these big new machines, often fairly quickly, is because they're using a community code. Now, the darker shaded ones are ones in which typically Argonne people have contributed to the code and continue to contribute, because these are open source community codes, and in which we have expertise, so we can help people get started and help them choose which one to use. You know, is NAMD the right one, or is LAMPS the right one for a particular project? So community codes, very important. So I think I've said it enough times. Moving data in various ways is a big issue, has been, and definitely will be in this next transition, say, to exaflops. And it impacts the energy use, because most of the energy is used in storing and moving data. So, you know, when we worry about having these huge electric bills, it's partly because of that. I mentioned that it bothers me that people worry more about scaling than wringing the most performance they can out of each core, and so that's something that we can do something about. And I try to do it by chiding people who say, oh, I've got this great parallel scaling, and then I ask them, well, what fraction of peak did you get? And the answer is 2%. So that's a good start, but not good enough. Resilience is going to be more of an issue, because when you have 1 billion cores, or at least hardware threads, that's a lot of stuff to keep working. But even as early as 1993, Jim Demmel at Berkeley wrote a paper that's very relevant to how to deal with faults. And so, in my view, the key issues in general have not changed that much. How to do a balanced architecture, how to have big enough memories that you can access fast enough are the key issues, and how to program things. So what I'm hoping for is that we spend more time investing in algorithms and investing in compiler technology, and investing in these ahead of time, so that there's some possibility, some opportunity for doing co-design, instead of just waiting until the system is in place and only then starting to change the way we do things. So more investment would be good in that area. Of course, one of the exciting things about having these big new machines is you can do something you couldn't do before. The bad thing is you don't know how to do it yet. And so, and furthermore, mating multiple modules that do different physics for one integrated simulation is really tough. You want to do ocean and atmosphere modeling, but the time frames, the energy transfer constants are very different between the two. And so knowing how to put together individual simulations, each of which is complex, but naturally run at different time scales, different dimensions scales is difficult. So that's going to be very difficult. Well, maybe if we have a long enough horizon, we could do something different. Well, so we could go back to analog computing. So here's Frank Morehouse. Argonne designed and built a number of analog computers, and they are really fast if you're solving ordinary differential equations, for example. Now you can see on the left there's a lot of spaghetti there of wires, because the way you initially would program them is by, by wiring them for each problem, each algorithm. But then there was such a thing as a hybrid digital analog computer, and several were built, including at Argonne, in which now you have essentially an electronic patch panel, so you can use the digital part to do the programming instead of physically having to do it by hand, less error prone and faster. And so, there's this decision diagram of, do you go along the top, which is going to be digital, or do you go along the bottom, which is analog? And Frank Morehouse's picture was in that previous photograph, did this lovely analysis that I happened to get from a colleague. It's never been published in the open, but it's about 20 pages of a very nice analytical analysis of comparing what at the time made sense of choosing analog versus digital. Another technology, maybe more promising than analog, though, is simply using something different than the CMOS circuits we've been using for a long time. And so we tried using RSFQ, rapid single flux quantum computing, in the late 90s. In fact, one of the projects that was funded by several agencies and that I and Thomas Sterling were involved in was called HTMT, and it used that kind of technology for some of the circuits. Now, we never got to build the whole thing, but we did get to build a simple circuit that I had at supercomputing, and it was running at 100 gigahertz. Of course, we had to have liquid nitrogen brought in, but cooling isn't that much of an issue. So you can go 1 to 200 gigahertz easily with RSFQ. Cooling is not as much of an issue as it used to be, and the power consumption is very, very small. So it's no surprise that NSA has been looking into that again. So I was glad to learn that even though it was abandoned in the late 90s, early 2000s, it is now being looked at again. Now, there are real issues. There are lots of advantages, but as you might imagine, balance, which I said was so important. So what kind of memory do you use? That's still an open question. So, maybe someday this HTMT, this is a poster from long ago, some version of that will exist. We tried to achieve balance through a different kind of all optical network, and lots of things to stage and hide latency, but it never got built. So the reason I bring that up is simply, let's try to think beyond CMOS, because we know that's near the end. Quantum computing, I'm not going to say anything about other than, it looks like at the fabrication level, there's some promise, and there are lots of very interesting articles in a recent issue of Science magazine. And I'll skip those things. So to me, it's been exciting to be a part of scientific computing for about 4 decades because of the end result, wonderful applications. And it's been enjoyable to work in multidisciplinary teams, learn things from them. So those are the factors that I see as being important. advances in algorithms and methods. Since I used to be a mathematician, I used to do a little numerical analysis. Community codes have really contributed, and software engineering, as well as the faster computers. I'm probably simplifying too much, but I really believe that there are a lot of things that can be done by looking at the lessons learned of the previous 4 or so transitions as we look ahead to the next 10 years. And instead of just saying we have to throw everything out that we've done before, let's think about, well, which parts do we really need to throw out and how we do things, how we program them. I think we just need to take a longer-term view. I know it's hard to do. We think about internet speed and everything, but sometimes it takes a while. Some things do take decades to mature and be useful. And it shouldn't be the same effort that's worrying about 5 years from now, because you can't do both in the same project, in my view. Also, as a computer science community, we should quit circling the wagons and shooting inwards. Bill Wolf came up with that, and I think we still do some of that. So, for example, people are saying, well, big data is the future, and it has nothing to do with high-performance computing. Actually, it has a lot to do with it. I'm not saying that everything in big data requires a big computer, but in fact, a lot of the methods that we find useful and even necessary for high-end computing are going to be very useful for big data, and high-end computing produces a lot of big data that we need to mine by the same techniques. So I'll end with what I think is the good news. I'm an optimist, and so I think there will continue to be a lot of progress in results to science and engineering, even though we're facing a disruptive next decade or so. Thank you very much.
We have a couple of minutes for some questions. Does anyone have questions for Dr. Messina? We also have an Adobe Connect session open. Questions, anyone? Steve Sims?
So one of the things that came out of, one of the things that came out of the Fast Forward project that is a file system that I'm very happy about was Lustre. Right now, you have the Fast Forward project, and a lot of the original Lustre guys are working on this project. Both Lustre and this Fast Forward project seems to be focused on defensive IO, being able to grab data very quickly. Now, I'm not trying to assert that big data and APC are orthogonal, but from my perception, big data is much more about reading large data sets, a la Hadoop, or rather than Cosmology or simulation, just taking those large data sets and making them. Do you care to comment on that?
Yes, so I tried to allude to it, but I gave no details at all. Certainly the access patterns are going to be different between the simulation data and the other kinds of big data that people talk about, where perhaps you have a lot of very small records, and it's complex data of very many different types as well, as opposed to relatively homogeneous data, as it would be the case for the typical simulation output. So the access patterns are a crucial difference, which also means that you want to optimize different things. But the ability to store affordably large amounts of data is common, and the big systems also happen to be pretty good at large graph walking, and so that's something that you end up doing quite a bit with the Hadoop type of analysis. So I agree that it's not one is a subset of the other, but I think there's enough commonality, and so even techniques like having the metadata available in a convenient way, I think has some common elements in the two kinds of large data archives. being able to promise that for the next 5 decades, some archive of data will be available. Of course, there are political issues there because the federal agencies don't want to have this long-term mortgage for maintaining it. But there are technical issues as well, as you know. So I don't know if that addresses your question at all, but I agree there are differences, but I just think we should look at both, and we'll find some commonalities as well. Now, the fast forward is more narrowly focused. I agree with that.
Any other questions? Suresh?
You mentioned about like some of the applications, different applications taking different power, and also you're trying to touch upon alternative to CMOS and so on. So I'm just wondering, will we see an era where there'll be more mathematical specific hardware coming out like FPGAs, and like neuroscience community promise that to promise neurons at a lower level, or such that the graph theories are coming in. So do we see that if you want to do PDEs, like, you'll use this hardware which has more built-in software functionality into them, into this kind of a thing, especially because industry is kind of pushing this a lot, like than before, like a graph theory, social networking coming in. Do you envision seeing any hardware evolutions coming out of this in this area?
I'm sorry, I'm not quite clear on your question. Hardware architectural changes, or?
Yeah, hardware architectural changes. Like, let's say if we want to do PDEs, like, will we have specialized kind of hardware, like, specialized for the neuroscience guys? Like, for instance, I think neuroprocessors, I think at some point, like, they were designing how, based on how the communications go on. Similarly, graph processings were like, the GPUs, when they were trying to customize at the FPGA level. So I was wondering, like, what do you see the CMOS alternatives at the hardware level based on application changes?
Well, for the foreseeable future, I mean, just in the next few years, I think we'll continue to have 2 basic architectures, one in which each node will have many, many cores of I'll say a normal CPU type of flavor, and then the one in which each node will have CPUs and then the GPU type architecture. In my view, there isn't a huge fundamental difference between them because you have to deal with parallelism up to a certain level, and then you'd have to specialize as to which one you're using. I think you were mentioning PDEs as a big driver, and traditionally they are, but there are many different kinds of applications that are being run on both kinds of systems nowadays. So I think what we're seeing now is simply people trying to get away with what they can afford in terms of how much memory per node and how many nodes they get, and just unfortunately putting up with it, regardless of a very deep analysis of what the applications are that are going to run. But in almost every case, these big systems are open to the world or to a large part of the world, and so you have to come up with what seems like a reasonable compromise of architecture. And some of the limitations, like memory size, are simply dollar-driven. They're not based on an analysis, this is good enough. For PDEs, I can come up with a reason. You can do the 3/4 power scaling, which tells you you don't need to scale memory size at anywhere near as much as the flop speed. But that's a special case for certain PDEs.
Ladies and gentlemen,